Today I'm gonna to present the modeling user fatigue for sequential recommendation. And this work is actually a collaboration between Tsinghua University and Kuaishou. The first question is, what is user fatigue? There are many definitions of fatigue, such as user feeling tired from prolonged use of Kuaishou. In this work, the authors focus on this phenomenon. Users are tired of the recommendations that are too similar to the content they have been exposed in a short historical period. As shown in this illustration, you can find out that users might initially enjoy watching videos about health, such as to avoid cancer, remember these 10 tips. However, when similar videos rapidly appear, users may gradually feel tired. We observe direct evidence of user fatigue on the Kuaishou platform. As shown in this figure, we plot the normalized effective view-through rate, EVTR, as a function of the number of effective views of videos with the same category in historical consumption. You can find out that the EVTR of videos with the target category decreases significantly when users have too many effective views of the same category. This is obvious evidence of user fatigue with respect to the repetitive consumption of similar videos. This issue can harm user experience and further reduce platform activity. How can we model the phenomenon of user fatigue? We conduct our research from 3 aspects. The first one, what features support the modeling? Second, how user fatigue influences user interests, particularly in the context of sequential recommendation. The third one is how to obtain explicit fatigue signals to supervise model learning, right? 3 things. In existing works, some studies manually extract a large number of repetition features, which represent the number of times a target item appears in the history consumption sequence, including the occurrences of item itself and its category. Those coarse-grained features are directly input into basic recommendation models to model user fatigue, but it is coarse-grained. Some studies also directly model the impact of user fatigue on interests. This approach maps the similarity feature between target and historical items to the influence of fatigue through a quadratic function, and combines this with a base model score to obtain the final score. So the quadratic function is used here to model the nonlinear effects of user fatigue. But we do think this is not enough at all. So in this week, the author proposed FRAC. First, we construct fine-grained features to support the modeling of user fatigue. We calculate the similarity between target and historical items in the latent space, considering that user fatigue can vary across different sub-interests. We compute this similarity for each sub-interest. Specifically, the first step involves extracting multiple interests from historical interaction sequence using a self-attention mechanism. And in the second step, for each interest embedding, we calculate the similarity between the target item and the historical interaction items with respect to that interest, as illustrated on the right. We call the similarity features as interest-aware similarity metric. So here, ISM, it is a metric, not a score. Based on ISM, we model the impact of user fatigue on long-term and short-term interest. Specifically, the first step is to perform feature crossing on ISM to consider the nonlinear mapping from similarity to fatigue. So the first step is basically learn some nonlinearity. The second step is to map ISM, this metric, to the weights of multi-interest fusion and obtain the long-term interests, which is estimation. The third step is to use ISM, this metric, as input to influence the gated units of GRU, thus modeling the impact of fatigue on the evolution of short-term interests, which is modeling. To obtain explicit fatigue signals, we hypothesize that the user fatigue increases significantly when the number of items similar to the target item in the user's historical interaction increases. Specifically, we try to replace several items of historical sequence with the target item and use both of the original and augmented sequences for contrastive learning. But remember, this one is not the positive one, it is a negative one. So the objective of contrast is the level of fatigue obtained from ISM. Now, let's take a look at the performance of FRAC. We used 3 datasets, 2 offline datasets, one being user click behavior on Kuaishou over a week, and the other one being user page view behavior on Taobao over 9 days, and one online dataset, which is continuous behavior of tens of millions of users over 1 hour collected from Kuaishou. Compared to baseline methods, FRAC achieved significant performance improvements, including in AOC and ranking metrics. Additionally, the training time for FRAC is comparable to that of the baseline method. So actually, we can conclude that FRAC is very significant and very effective. In ablation study, we find that on the Kuaishou dataset, the performance drops the most when contrastive learning is removed. But this is not the case for the Taobao dataset. Why? We attribute this difference to the effectiveness of sequence augmentation for obtaining fatigue signal. In Kuaishou, a micro-video platform, repetitive recommendation of the same videos obviously will cause intense user fatigue. However, for e-commerce platform like Taobao, multiple views of the same product page are relatively common for us, and the users may not experience fatigue during limited repetitions. In contrast, ISM plays an essential role in interest evolution on the Taobao dataset. This demonstrates that the effectiveness of guiding short-term interest evolution with ISM as necessary inputs for update and reset GRU gates. So it can be explained by the intention changes of sequential behaviors in the e-commerce applications. Specifically, users have different intentions when browsing the products, and they may experience fatigue of redundant exposure if the intention has switched. We further deploy FRAC on Kuaishou to verify the effectiveness of fatigue reduction and satisfaction improvements. We first show a recommendation case for a user. The user has watched many sports videos recently. You can find out that. FRAC ranks the basketball video in the last position. This demonstrates that FRAC can elevate improper and repetitive recommendations that may cause user fatigue in a period of short time. Besides, as a part of user interest, the video about the trips lies at the top, with which the user has limited interactions. So FRAC is more diverse in this case. And we have A/B tests on Kuaishou. You can find out that This A/B test also demonstrates that FRAG not only enables users to spend more time on the platform and view more videos, but also prevent similar videos from clustering together. So very impressive, right? In order to further demonstrate the effectiveness of fatigue reduction, we conduct a similar analysis shown in the 3-page. It's obvious that FRAG can improve EVTR significantly when users have consumed many similar videos. Finally, we would like to explore the differences between diversity, novelty, and user fatigue. Specifically, diversity is something typically focuses solely on the dissimilarity between items in the recommendation list. This one irrespective of users' historical interactions. On the other hand, novelty emphasizes that the recommended items are unknown to the user, characterized by their divergence from historical items or by the item's popularity. In contrast, user fatigue represents the negative aspects of user experiences, influenced by the target historical similarity. To conclude, FRAG models user fatigue from 3 aspects. The first one is what features support the modeling? ISM, right? The second one, how user fatigue influences user interests, some like Kuaishou evidence. The third one is how to obtain explicit fatigue signals to supervise model learning, FRAG. You can scan the QR code to access the paper and code. Well, that's all. Thank you.